Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about low-rank models, which are a very important statistical model to deal with matrix-valued data, such as, for example, datasets where we have ratings given by users to a set of movies. We're going to explore the connection between low-rank models and principal component analysis, and we're also going to show how to use these models to extract interesting patterns from real data. Let's get to it. We're going to talk about low-rank models, and here the motivation is that many data sets have this structure where each data point is associated to two entities. For example, in recommender systems, the data could correspond to ratings given to a movie I or a product by a user. In computational genomics, this happens a lot, where we might have some kind of measurement of a gene within a cell for many genes and many cells, for example, expression levels. In weather forecasting, you could have this situation, and we're going to see a data set exactly like this at the end of the video, where you have temperatures at certain locations and certain times. This kind of data can be naturally thought of as a matrix where one of the entities corresponds to the columns and the other entity corresponds to the rows. In this case, in this toy example that we will be analyzing during this video, the data correspond to ratings given to movies by these four users: Bob, Molly, Mary, and Larry. Okay, for example, Bob didn't like The Dark Knight, but really liked Bridget Jones' Diary. And we're going to see how to analyze this type of data with low-rank models. We're going to dive right in, and I'm going to just begin explaining low-rank models, showing you an actual low-rank model, because I think that's the best way of gaining some intuition. So what do we do in a low-rank model? And this is a very, very, very basic low-rank model where the rank is 1, and we will see what we mean by this in a moment. Essentially, what we say is we can express the ratings, each rating as the mean rating plus a component that depends on the movie associated to the rating and the user associated to the rating. And the assumption we make is that there is a certain pattern common to all movies. Okay, notice this pattern is common to all movies. And then to get the rating for each user, what do? We multiply a coefficient corresponding to each user to that pattern. So Bob's coefficient is 3.74. We multiplied with the pattern for all the movies to get the rating for Bob, and then we add it to the mean rating. For Molly, actually, the coefficient is very similar to Bob, so it seems that Molly and Bob like the same kind of movies, but you can notice that for Mary and Larry, the coefficient is completely different. So this pattern is going to be inverted for them. They're going to basically dislike the movies that Bob and Molly like, and they're going to like the movies that Bob and Molly dislike. This is a pretty strong assumption, right? The fact that you can express the rating of a user for all the movies as a fixed pattern that is just scaled by a single number. But that's what a rank 1 model does. The advantage of this is that we have expressed this matrix of ratings with many less parameters. So here we have 4 users and 6 movies, so 24 data points. Our model here, let's see how many parameters it has. It has 1, because it's the mean rating. Then it has 6, which is this pattern of this fixed pattern. And then we have 1 coefficient for each user, so that makes 4. So in total, we have 11 parameters that explain the ratings, assuming that we can explain the ratings with this structure. Notice that I could have made exactly the same argument the other way around, and this is something interesting about low-rank models, because I could have said, well, actually, what I have here is a fixed pattern for the users, and then the way I get each movie is by weighting by this coefficient, okay, which is different for each movie. Okay, so there's a symmetric thing going on here where we can interpret the rank 1 model in two ways. We have a fixed pattern of ratings that we weight in different ways to get the rating for each user. I meant a fixed pattern of ratings for the movies. Or we have a fixed pattern of ratings for the users, which is here in pink, that we scale with different numbers depending on the movie. So this is an example of a rank 1 model where we have a single, let's say, pattern for the movies and a single pattern for the users. In general, when we have more complex data sets, we want to have several patterns for the movies and several patterns for the users, which will increase the number of parameters, but still keep it much smaller than we had like just the original matrix, as I will explain in a moment, and that is called a rank R model. Okay, so in a rank R model, we make the assumption that the data depends on a small number of factors, in fact, R factors, and what we do is we set things up in exactly the same way as we saw for the rank 1 model. So just to clarify, in the rank 1 model, we had this pattern, which was for the movies, if you remember, and this pattern that was for the users. But now what we say is, okay, this is too simple to express, to capture the structure that we want to capture from the data. So what we do is we add some additional, well, maybe I'll use the same color, some additional patterns here. So instead of having only one, we have R, okay? And the corresponding patterns for the users. So at the end of the day, if you look at what the estimate for the rating is going to be, well, we add all of these patterns, and typically we would add it to a mean rating. So here we would have plus the mean rating, but to simplify matters, we're going to assume that everything is centered by subtracting the mean. I will talk about this centering business a bit more later on. And essentially, the estimate or the model for the rating corresponding to the ith user and the jth movie is obtained by taking these entries of the movie pattern. Actually, this would be the ith movie and the jth user, just to keep it consistent with the example that I just showed you. The way we get the estimate of the rating for the ith movie and the jth user is by taking each of these coefficients corresponding to the movie and multiplying it by the corresponding coefficient by the coefficient corresponding to the user, and then adding them to the product of the remaining coefficients for the movie times coefficients for the user. You can see here that the parameters of the model are going to be R times the number of movies. Of course, here I'm talking about movies and users, but this could be applied to genomic data, temperature data, etc. And here it's R times N times the number of users. So this is R times N the number of movies plus the number of users. On this side, we have N, the number of movies, times the number of users. Okay, so when the matrix is very large, the low rank model really reduces the number of parameters that we're using to express the data. Okay, I know that the things get a little bit complicated. Hopefully that made it more or less clear what the structure of a low rank model is. Okay, so we can interpret, again, these coefficients on the left as the contribution of the factor L to the movie I. In our example, we had a single factor, so that single coefficient captured the contribution of the movie to that factor. In a rank R model, I just want to emphasize, we have several of them. On the other hand, on the other side, the coefficient on the right here captures the contribution of the user to that same factor. And these two contributions get multiplied and added to the other factors to form the low rank model. Why do we call this a low rank model? Well, if you remember your linear algebra, if you consider a matrix like this that is obtained by multiplying this matrix and this matrix, what's going to happen is that each of these columns here is going to be a linear combination of these columns dictated by these coefficients, okay? That's linear algebra. If you don't remember that, maybe you can review matrix vector multiplication in this case. You take this matrix multiplied by this vector, you're going to have a linear combination of the columns of the matrix, and that's going to give you this column. So basically this shows us that the columns of this matrix, if the equality holds, are equal to a linear combination of R columns. Okay, so there are only R independent, linearly independent vectors that span all the columns of that matrix, of the matrix obtained by multiplying these guys. So that matrix has rank R. Equivalently, the rows, okay, and here I should have put equality, okay, and here maybe I should have put L. So the low rank matrix obtained by multiplying these two guys, the rows are going to be linear combinations of these rows governed by this coefficient. So this would be the coefficients for the first one, okay, and because the rows, if you look at the row space, which is basically the subspace spanned by all the rows of this matrix, they're all linear combinations of these R rows. That means that the matrix has rank R. Okay, so basically what we do when we fit a low rank model is we say, okay, in order to explain this data, in order to fit a model to this data, we're going to assume that in reality, the columns, the degrees of freedom, if you want, in the columns are just R. All the columns can be built as linear, or approximated at least, as linear combinations of just R vectors. And at the same time, because of the structure of matrices, we're also assuming that all the rows can be built as linear combinations of R row vectors. Okay, so that's the rank of that matrix. Now, how do we fit the model? Well, as I just said, essentially what we're doing when we're fitting a low rank model is expressing each column as a linear combination of R columns. So now the problem is, how do we choose a set of R vectors so that when I express all of these columns as linear combinations of just those R vectors, I preserve as much structure as possible? Okay, and what is the best way of finding R vectors that can express a data set of d-dimensional? Here, this will be the dimension d, okay? So we assume that dimension d is much larger than R, and we want to find just R vectors that can express all of these d-dimensional vectors and preserve the structure as much as possible. This should sound familiar if you've seen the video on principal component analysis, because actually principal component analysis allows us to obtain an optimal basis of vectors to preserve as much structure as possible, in the sense that they will approximate the original vectors optimally in terms of L2 norm. You can go look at the video on dimensionality reduction, but basically in principal component analysis, what do? We build the sample covariance matrix of all of these columns. We take the eigen decomposition, and the eigen decomposition gives us this basis of eigenvectors, which are the principal directions of the data. We choose the eigenvectors associated with the largest eigenvalues, and those eigenvectors enable us to perform optimal linear dimensionality reduction. So if you remember, the way this is achieved is by taking the inner product of these principal directions with each of our data vectors. We assume, by the way, that everything is centered. Okay, we have centered the columns removing their mean. If that is the case, then the principal components are obtained by taking the inner product of the data. These are the columns of my matrix. Here I'm using this Python notation. So this is the jth column of the matrix. We take the inner product with each of the principal directions that are associated with the largest eigenvalues of the sample covariance matrix. And that gives us an approximation where we take that coefficient that we just computed and we use it to scale the principal directions. That gives us a lower dimensional approximation because it's going to be a linear combination of just the first, in this case, R principal directions, which preserves, again, as much L2 norm as possible. And we didn't prove it in the video, but it's proved in the book if you want to take a look. That is optimal from that point of view. Okay, this is going to preserve as much energy as possible in the data. So let's go back to our low rank model. This approximation of the columns of the vector, which again is obtained by, so I'm just going to highlight here. Imagine we want to estimate this column. The way we can approximate this column is by taking the principal directions obtained from the eigenvectors of the sample covariance matrix of the columns of this matrix and scaling it by the corresponding principal components. Okay, and this is optimal in the sense of preserving the structure in the columns of this matrix. And you might have realized that this actually gives you a low rank model where the left coefficients corresponding to the factors are the principal directions and the right ones are the principal components, because we can do this for each of the columns. So we're going to get coefficients for each of the columns here. And we have exactly a low rank decomposition or approximation of our original data matrix. So principal components actually allows us to fit a low rank model. You might be wondering, but wait a minute, why did you do this for the columns? Because you could easily also have done it for the rows, right? And the answer is yes, absolutely. You can completely do this exactly in the same way for the rows, where now what we say is, well, we want to express the rows of our matrix as a linear combination of R vectors to obtain a low rank approximation to the data matrix. And indeed, you can do that. And then you can ask yourself, how do I obtain the best R dimensional approximation to all of the rows? How do I pick these R vectors that span the best subspace that allows me to approximate all the rows in this matrix? And what is the answer? Well, you apply principal component analysis on the rows of the matrix. Okay, so exactly the same idea. You apply PCA, you take an eigendecomposition of the sample covariance matrix, this time of the rows. And now the principal directions, which are obtained as the eigenvectors corresponding to the R largest eigenvalues of the sample covariance matrix of the rows, that is going to allow you to obtain a low dimensional representation of each row that is achieved by first computing the principal components as the inner product between the row and the first R principal directions that correspond to the largest eigenvalues of the sample covariance matrix, and then multiplying again by those principal directions to obtain the low dimensional approximation of the rows. And you do this for every row. And when you do that, I'll show you the picture, you get this approximation where you're taking a linear combination of these principal directions of the sample covariance matrix of the rows, and you scale them by the principal components of each of the rows. If you stack the principal components like this, you immediately see that you have another low rank approximation of the original data matrix. So now you might ask yourself, oh, by the way, something that I should have probably highlighted is that here we're assuming that the rows have been centered by removing the mean of the rows. So this is different to what we're doing with the columns, right? In the columns, we were removing the mean of the columns. And this is, just to be clear, the entry-wise mean. This is just the sample mean of a data vector. Okay, so which one is better? Is it better to apply principal component analysis to the rows, or is it better to apply principal component analysis to the columns? Well, the answer is that it's completely equivalent. Up to centering, because remember that when we're doing it to the columns, we were subtracting the sample mean of the columns, and when we're doing it to the rows, we're subtracting the sample mean of the rows. So that's a different operation. You can actually do something that is double centering, so that both the columns and the rows are centering, but I don't want to get into that rabbit hole. But the point is that up to centering, if we ignore the centering operation for a moment, it's completely equivalent to do principal component analysis on the columns or on the rows. And in order to understand why, we're going to introduce a very important tool from linear algebra, which is the singular value decomposition. So I don't have time in this video to delve into the properties of the singular value decomposition, but they are explained in the book. But basically, every matrix, every real valued matrix, is going to have a singular value decomposition where we express the matrix as a product of three matrices, U, S, and V transpose. The matrix here on the left, U, has columns. Well, I'll start with the one in the beginning because that's how I did it here. The one in the center, I mean. This matrix in the center is diagonal, and each of the entries of the diagonal is a positive number, or non-negative number, rather, I should say, that we're going to consider is ordered, okay? S1 is larger or equal to S2, larger or equal to SR, and they're all non-negative, okay? Why do I have R here? Because originally I had written this with some zeros here at the end. Just in full disclosure, if you put some zeros here, then the matrix has rank equal to the number of non-zero eigenvalues. Not eigenvalues, singular values, which is what these guys are called. And this is why I have an SR here. I should have modified the slide. Sorry about that. But anyways, okay, so we have this matrix in the center that has all the singular values. Then we have a matrix on the left that has what we call the left singular values, which are orthonormal vectors that span the whole column space of this guy. Okay, so the column space of this guy can be expressed as a linear combination of these column vectors. Conversely, the row space of these guys can be expressed as linear combinations of these vectors that we call the right singular vectors, which are also orthonormal. Just to remind you, orthonormal means that they are perpendicular to each other and they have unit norm. Here we have a transpose because these guys are the rows basically that span the rows of this guy, of the original matrix. Every matrix has a singular value decomposition. You can actually prove this from the spectral theorem. You remember the spectral theorem says that every symmetric matrix has an eigen decomposition where the eigenvectors are orthonormal vectors. And you can take a look at the video on the proof of that result if you don't remember it. Okay, but the point is that every matrix has a singular value decomposition. But what is the connection between the singular value decomposition and low rank models? Well, the connection is that you can actually, and maybe this is not completely obvious to you at a first glance, and if it's not, maybe you can just sit down and kind of see that this is indeed true. But if you perform this product, this equivalent to taking this column of the left matrix, multiplying it by this number in the diagonal matrix, the first one, and then multiplying it by V1 transpose. Okay, then you take that and you sum it, and that gives you a matrix that is going to have the same number of rows as the entries here and the same number of columns as the entries here. Okay, so exactly the same dimensions of this original matrix. If that is not clear to you, that U1, S1 is just a constant, U1 times U1 transpose, which looks like this. If it's not clear to you that that's going to give you a matrix with the same dimensions as this matrix on the left, then, I don't know, work it out and you will see that that is indeed true. To do the full product, then you sum that matrix with a matrix that is obtained by taking U2 times S2 times V2 transpose, and then you sum it to another matrix, which is U3 times S3 times V3 transpose, and so on. Okay, so this is linear algebra. It gets a little bit complicated, but this is true, basically. You can express the matrix on the left as this sum, okay, where n1 is the number of rows, which we're assuming is smaller than the number of columns. Otherwise, it would be the number of columns of these matrices that have the same. So this guy has the same dimensions. We're going to show a picture in a moment as this matrix on the left. And it just so happens that these matrices that are formed by taking UL times VL transpose, maybe I should have written a transpose here. Okay, this is VL transpose. These matrices have interesting properties. They are rank 1, which kind of should be obvious here because basically every column is a scaled version of UL and every row is a scaled version of VL. They are orthogonal, and here orthogonal I mean with respect to the Frobenius inner product between matrices, which sounds very scary, but at the end of the day, it's just basically what you the inner product that you get if you stack all the entries of the matrix as a really long vector and take the inner product with another matrix where you also stack all its entries in a very long vector. That's the Frobenius inner product. According to this inner product, K1, K2, K3, and so on, they're all orthogonal, which makes a lot of sense because these guys are orthogonal by the properties of the singular value decomposition. And finally, each of these guys has unit norm. Again, this norm is the Frobenius norm, which is obtained by taking the norm of the vector that is the result of stacking all of the entries of the matrix in a very long vector. Why do I say this? Because then now you can think of these guys as just orthogonal vectors in a way. I know there are matrices, and here I mean vectors in a very abstract way. Okay, but components, if you are more comfortable with this, they are orthogonal components where the norm or energy of this whole matrix is basically the sum of the squares of, oops, sorry, I thought I was going to highlight there, and I really didn't, of the singular values. So basically the singular values are telling you how much energy each of these rank 1 components contributes to the whole matrix. And remember that they're ordered. So S1 is going to contribute the most energy, then S2, then S3, then S4, and so on. So what if you want to get a rank R decomposition, like let's say a rank 2 approximation to the original matrix? What should you do? Well, this suggests that you should just keep S1, S2, and their corresponding rank 1 components, K1 and K2, and kill the rest. And that's exactly, oh man, this was the question I was answering now. How do you get a rank R approximation from this? Well, basically the way we do it is we truncate the SVD. So we say, oh, okay, we're going to stop here at, let's say 2, if we want a rank 2 approximation, or 10 if we want a rank 10 approximation, and throw away everything else. Because we know that these singular values tell us the contribution of each of these components to the original matrix, and we want to just preserve the ones that have the largest contributions. Okay? And again, this kind of makes sense because we can interpret these guys as unit unit norm orthogonal vectors. And here by vectors here I mean just like in a very abstract way, like matrix components, if you want. So now we're going to see the connection between this low rank approximation obtained by truncating the singular value decomposition and principal component analysis. Well, it just so happens that if the columns are centered and you do the product D transpose, then that is actually the sample covariance matrix of the columns. And because of this, and this is not immediately obvious, but you can take a look at the book for the details, because of this, the left singular vectors in the SVD, here I'm just showing you the first R ones, because I've already truncated, I've already thrown away everything that didn't correspond to the first R components of the SVD. These first R singular vectors are exactly the same as the first R principal directions of the columns of the matrix, because the sample covariance matrix of the columns is equal to DD transpose. Okay, and if you compute it, you will observe that essentially the matrix that you get on the left of the SVD is going to be exactly the eigenvectors of this sample covariance matrix. Okay, so that means that these principal components on the right are actually equal to, and again, this is not immediately obvious. When I say that means, you have to work it out, but you know, it's not that complicated. And here I just want to give you the intuition. This is actually exactly the same. So when you multiply the matrix of singular values times the matrix of right singular vectors, you exactly obtain this matrix of principal components that we have talked about when we were talking about applying PCA to the columns of the data matrix in order to obtain a rank R approximation. So basically, this truncated SVD is the same as applying PCA to the columns of the matrix, as long as the columns are centered. Maybe this won't come as a surprise. It turns out that D transpose D is equal to the sample covariance matrix of the rows. So now if you look at the right singular vectors in the SVD, in the singular value decomposition, they are exactly the same as the principal directions of the rows of the matrix. So when you look at the principal components that we have obtained from the rows, they're exactly the same as taking the left singular vectors and multiplying them by the singular values. So, and again, all of this is not obvious, you have to look at the derivations, but the reason is mainly that the sample covariance matrix of the rows is equal to D transpose D if the rows are centered, and because of that, the SVD up to centering, the truncated SVD is exactly equivalent to performing PCA on the rows. So our conclusion is that truncating the SVD, applying PCA to the rows and applying PCA to the columns is completely equivalent up to centering. The centering operation that you actually apply will mostly depend on the kind of structure that you want to learn from the low rank model, and we will talk a little bit more about this a bit later. Okay, so, and something that I forgot to say but is really important, and this comes from the fact that PCA gives you an optimal low dimensional approximation of the columns and of the rows. It turns out that because of this, and the proof is not obvious, the proof is in the book, if you do truncated SVD, you obtain an optimal low rank approximation of the entries of the matrix in this Frobenius norm, which is actually equal to, the sum of squared entries. So if you look at the squared errors per entries and you add up all those squared errors, the optimal rank R approximation is obtained by just truncating the SVD. You cannot get a better rank R approximation. Okay, so we have been talking a lot and showing you a lot of formulas and so on. Let's look at an example. Let's go back to our movie ratings example. So here we had this matrix with 24 entries, and we wanted to obtain a good approximation with low rank. Here we have so few entries that we're going to choose rank 1. Typically, and we will see this in a following video, you would use a higher rank to represent this kind of data, because you would think that there are multiple factors that affect the ratings of users and movies. But here we're going to, we have a very small example, this cartoon example, so we're just going to fit a rank 1 model. What do? We start by centering. In this case, we will just remove the mean rating, okay, which is equal to 3. We remove that from every entry, and then we compute the SVD. And what do we find? We find that in the SVD, the first singular value, okay, of this central singular value, diagonal singular value matrix is much larger than the rest, which indicates that indeed this data can be well approximated as a rank 1 model, because you can see that the contribution of the first component in this singular value decomposition is much larger than the contribution of the remaining components. So what are we going to do? Basically, we're going to say bye-bye to the remaining components, which means that from here we're just going to preserve the first column, and from here we're just going to preserve the first row. And this is exactly the rank 1 model that I showed you at the beginning of the video. This is how we obtain it, by truncating the SVD. And now from the rank 1 model, we can learn a little bit about the users and the movies. But before that, forgot. Now we can actually ask ourselves, how well does the rank 1 model, we're going to do this thing of interpreting the movies and the users in a moment. Sometimes I forget the order of my slides. So first we're going to see how well we approximate the original matrix. That's always a good thing to do. So we're going to basically take this guy, multiply times that, and then add back the rating, which we had subtracted at the beginning. And that gives us this model. And you can see that, the approximation is actually not bad at all. So maybe just very quickly, these are the large entries. You can see that the approximation is pretty decent. Of course, not perfect, because we're expressing 24 numbers as a function of a smaller number, which was, let me remind myself, 6 plus 11, I think it was. Was it 11? Let me just check very quickly. 1, 2, 3. So yeah, so there's 6 of this, 4. Okay, so that's 10 numbers plus 1, 11. Okay. So of course the approximation is not perfect. Let's take a look at the smaller numbers. It's close but not perfect, but it's pretty good. And the advantage now is that we can, for example, cluster the movies according to which ones have similar coefficients in this pattern of movie ratings. So we see that The Dark Knight, Spider-Man 3, and Superman 2 all have similar coefficients. This means that they are similar movies according to the model, because they're going to be treated like, basically the ratings given to them are going to be constructed by multiplying the same numbers, right? So they're going to obtain similar ratings depending on those numbers for different users. And similarly, we have Love Actually, Bridget Jones' Diary, and Pretty Woman that are similar movies according to the model. And now when we go to the users, we see that Bob and Molly, the coefficient for Bob and Molly is high. So when multiplied with movies that have positive values here, this is going to add to the mean rating. So they really like these movies. Bob and Molly apparently like romantic comedies. And they don't like the other movies, because those movies have negative coefficients multiplied times these positive coefficients. That's going to bring down the rating for those movies, for all those movies. So they don't like superhero movies, it just so happens. On the other hand, Mary and Larry have negative coefficients. So this means that for the superhero movies, actually the rating is going to go up from the mean rating. So they like the superhero movies and they don't like the romantic comedies. For the romantic comedies, the rating would go down. And here you can see that this rank 1 model kind of captures a certain property of the movies. It groups users with similar ratings with respect to that factor, let's say. And here it groups different movies that are similar with respect to that factor. When we have a rank R model, we have several of those factors and they get added up to produce the final rating for a certain movie and a certain user. Okay, and here I was highlighting the coefficients for the users, but I did everything in the previous slide, so we're good. Okay, to end the video, I'm going to show you how to extract patterns from data using low-rank models. We're going to analyze a data set of hourly temperatures at 134 different locations in the United States over 1 year. We already used this data set when we're talking about the sample mean. These are the sample mean of the temperature at every location. So the circles are bigger, the higher the sample mean. So we can see here that in the south of the United States, it's much warmer than in the north of the United States. Okay, and that this is Hawaii. Hawaii is pretty warm. Not here, because this is at the top of the small circle is at the top of a very high volcano where it's colder. To complement this analysis, we had looked at the sample variance of each individual at each individual location, and what we saw is that there's a lot of variance in the interior of the United States and also in the east, and much less along the coast, and much less in Hawaii. Okay, but this was the sample variance at each individual location. Now we're going to try to understand if there's some like patterns, temporal patterns in the data that kind of that are common to different stations. This is what we're going to try to do. So we're going to center the temperatures at each station, removing the sample mean at each station. And this is what I meant earlier, that depending on what the goal of your analysis is, it might make sense to remove the sample mean of the columns. It might make sense to remove the sample mean of the rows. It might make sense to just remove the sample mean of the whole matrix, just of, the average of all of the entries, which is what we did with the movies. Or it might make sense to do double centering, where you do something to make sure that the columns and the rows are centered. This will depend on the goal of your analysis. Here we're interested in temporal patterns, so we're just going to remove the sample mean of the temperatures at each station, which means removing this number from each of the temperatures. So, like the temperature here, we will remove 3.84 from all the temperatures from that station, for example. Okay, so we're going to take, I took with Python the singular values, and you have this code online in case you want to take a look. When you compute the singular values of this centered data, you see that there's a large singular value that completely dominates. So there's very, very strong rank 1 structure in this data. And then there's a second singular value that is also very prominent. So today we're just going to explore those. It would kind of be interesting to look at the rest, and if anyone does, I would be very interested to hear the results, but I've just looked at those two first ones. Okay, so this first singular value, if we discard all of the rest, gives us a rank 1 model where we approximate the temperature at each station and each time as the mean temperature of the station, because this is what we have removed to perform our low rank analysis. So we have to add it back if we want to approximate the original data point, plus this low rank model where we have the first singular value, the left singular vector and the entry corresponding to that station, and the entry corresponding to that time of the first right singular vector. Okay, so then let's take a look. What we're saying is we can express the temperature throughout the year at a particular station by just scaling the same vector for all of the stations, of course scaling it by a different coefficient. So what should that vector look like so that it can represent actually the fluctuations over the year at many stations? What is this common pattern that should arise? I encourage you to stop the video and think about what it should look like throughout the year. And now I'm going to show you. So it looks like that. So hopefully it makes a lot of sense to you. What is this? This is just annual seasonality, which is, by the way, something that when you're doing climate analysis, you usually take away because you know that it's going to be there. Okay, so warm in the summer, cold in the winter, because this happens across many stations. So you can get a reasonable approximation to the temperature of the stations along the year by just scaling this pattern. This is not the end of the story, because you can also zoom in. And what do you think we're going to do when we're going to find if we zoom in day by day? What is a common pattern that you expect to find across different stations day by day? Well, what you find is something that looks like this. This is in April. And this is basically a daily pattern where in the day it's warmer, in the night it's colder, which makes a lot of sense. We see the same pattern in August. When we zoom in, we see the same pattern in December. And again, remember, this is this common pattern that is scaled by different coefficients at different stations to approximate the temperature throughout the year. So now we can look at those coefficients, and now maybe you can think, what coefficients do you think are going to be larger and what coefficients do you think are going to be smaller? Remember that this is the coefficient that is multiplying this seasonal pattern at different stations. So where do you think it's going to be larger and where do you think it's going to be smaller? Maybe pause the video and think about it. And now let's go. This is the component that kind of weighs the seasonal and daily pattern. So we see stronger, larger values for places which have a lot of seasonality. It's much warmer in the summer, much colder in the winter, and very small for places where there's barely any seasonality. Okay? Florida, Hawaii, and the coast of California. So that makes a lot of sense. Now let's take a look at the second, at the rank 2 model that incorporates also this second component from the singular value decomposition of the centered matrix. Let's explore it a little bit. So we're going to do exactly the same thing. We're going to look at this pattern that is combined with the first pattern, multiplying it by a different coefficient to build the rank 2 approximation to the temperatures. And now think about it and maybe pause the video for a moment and try to think oops, sorry, I completely spoiled that. But now maybe pause and think about it. And actually maybe I didn't ruin anything because I have no idea what this pattern is showing. And if anyone has a clever interpretation, I'm all ears. When we zoom in, we see something a little bit more structured. I mean, definitely more structured. We see this zigzag thing. So what is this achieving? Again, if you can think about this for a while, there is a solution that I'm going to reveal in a moment. It was a surprise for me. It's something that I hadn't guessed. Okay, so how do we find out what is going on here? How does this component enable us to get a better approximation to the temperatures when we scale it across different locations? Well, in order to find out how that happens, a reasonable thing to do is just look at what is the value of this coefficient at different locations. How do different locations weight this component differently? And that actually reveals a lot of structure. So here is the value of the coefficients. In black is when the coefficient is negative, and the bigger it is, the more negative it is. And in white is when the coefficient is positive. So we see that in the east, the coefficient is positive and large. In the west, the coefficient is negative and also large. And it's smaller when, in the coast here, where the first coefficient, remember this is important, it's smaller actually in places where the first coefficient was also small. So what is going on? What is this doing? In order to understand what this is doing, what we're going to do is we're going to take two examples, like Corvallis on the west and Kingston on the east, so Oregon and Rhode Island, and we're going to see how the rank 1 model differs from the rank 2 model for both stations. And here we see that the main difference between the two models is that the second component is weighted negatively in the case of Corvallis and positively in the case of Kingston. Their first coefficient is actually quite similar and their mean is not that different. Okay, so the main difference between them is going to be driven by this second component. Actually, it's not really true that the main difference, but there is a significant difference that is going to be driven by the second component, because remember that actually this guy could be much smaller. So what I'm saying is, of course, the mean here. So here the temperatures are typically going to be warmer than here, and here there's going to be more seasonality than here. Okay, so it's just to make this clear. But now we're going to focus on what difference that this induced. The fact that the second coefficient is negative in Corvallis and positive in Kingston. And for that, we're just going to visualize the data, the rank 1 model and the rank 2 model. And when we do that, we see first of all that the approximation is not bad for both, but that there's something quite interesting happening. The rank 1 model is this dotted line The difference between the rank 1 model and the rank 2 model is that basically the rank 2 model is shifted to the right. And here, the rank 2 model is shifted to the left with respect to the rank 1 model. Why is this? Well, basically, in Corvallis, what is happening is that the warmer, this, and this, by the way, is April, so this is day by day, so this is a day, this is a day. So this daily pattern of temperatures, where it's cold at night and warm by day, is shifted to occur later in Corvallis and shifted to occur earlier in Kingston, Rhode Island. Why does this make sense? Maybe pause the video and think about it. Well, because in Corvallis, the sun rises approximately 3 hours later than in Kingston, because Corvallis is on the west of the US and Kingston is on the east of the US. That's why we have different time zones. We actually observe this pattern also in August. Here, shift to the right. Okay, so warmth happening later. And here, shift to the left. Okay, the warmth happening earlier in Rhode Island because the sun rises 3 hours earlier. Okay, and in December, we kind of see that again, although it's a little bit noisier. But still, you see that this is to the right, and this goes to the right when we compare the rank 1 model to the rank 2 model, and this goes to the left. And that is why these guys have a positive component that shifts this daily pattern of temperatures to occur earlier, and these guys have a negative component that shifts the pattern of temperatures to occur later. So, and this is completely automatically extracted from the data using the low rank model. So hopefully this convinces you that we can extract very meaningful insights from datasets, matrix value datasets, such as this weather dataset, by applying low rank models. In this case, a rank 2 model. Okay, so what have we learned? We have learned how to interpret low rank models. We have learned about their connection to principal component analysis. And then we have learned how to fit them by truncating the SVD and how to use them to extract interesting patterns from real data. And that's all I have. Thank you very much.